All right, welcome to today's physics video. So continuing with our one-dimensional motion unit, today we're going to talk about free fall. Your learning targets are up here on the screen. So you should be able to identify an object in free fall, and you should understand how free fall affects the motion of an object. All right, so here we go. Bam. Oh, I said bam. There we go. All right, so before we learn about free fall, we need to learn about what's called a force, all right? And we're going to do a huge chapter on force in a little bit. So this is really just going to give us the basics. So the definition of a force is a push or pull on an object, all right? And we can numerically measure force, all right? So a large force means that the object is being pushed or pulled, hard, all right? How hard something is being pushed or pulled has nothing to do with how fast the object is moving. So please make sure that you separate those two ideas. Force and velocity are not the same thing. Okay. Basically, what we'll learn to do, or what we will learn, is that the goal of a force, like sort of what a force is trying to do, is to change the motion of an object in some way. All right. In general, a force will try to make an object speed up or slow down or turn. Okay, and then how quickly it does that depends on other forces and the mass of the object, and a bunch of other stuff. Anyway, we're going to talk more about forces next chapter. Before we do, though, or before I move on, though, let me talk about a couple examples of forces. All right, so here we go. Some different examples of forces that you should be aware of. People can exert forces, so you can have something like the force of Roy, or Carl, or Sally, or Hecker, or whoever. All right, you can have gravity. You see the force of gravity all the time. That's why stuff falls, right? When you hold a ball up in there and let it go, it falls because of the force of gravity. All right. Once we get into forces a little bit more, we'll talk about force of friction. At the end of the year, we'll talk about electrical forces. There are two types: electrical attraction and electrical repulsion. And we'll also talk very briefly about the force of air resistance. Okay. That, if you move through the air pushes against you, okay? And thus is providing a force. All right, so I think that's pretty much it. There's also objects can exert forces. Oops, force of an object. All right, so for example, if you imagine two boxes sliding along and then bumping into each other, when they bump into each other, they both push each other, right? They both exert forces on each other, okay? So anyway, we will talk more about that later on, all right? So anyway, a force is a push or a pull, okay? So here we go. So free fall, we say that an object is in free fall if the only force acting on it is gravity, okay? So that means no friction, no Roy, no electricity, no air resistance, okay? So free fall is, an object isn't free fall if the only force acting on it is gravity. Okay, so here we go. Let's talk about some examples. So the first example, I wish I hadn't grouped those all together. The first example is a ball that has been dropped, right? Obviously, when you drop something, gravity pulls it down, right? Okay. Now, even if you throw the ball, it turns out that after you release it, the only force on it is still gravity, right? So technically speaking, even if you throw a ball downward, it's still in free fall, all right? And for that matter, it doesn't even matter what direction you throw it. If you throw the ball up in the air, it's going to go up, slow down, stop, and then come back down, right? And the reason it's doing that is because gravity is acting on it. That's the only force in it, okay? So in all of those examples, the only force acting on the ball is gravity. And that's why their velocity becomes more and more negative, right? In other words, in the first example, the velocity began at 0, and then it moved down faster and faster and faster, so the velocity got more negative. If you throw something down, the same thing is true, that it speeds up how quickly it's going down. In the last example, when we threw it up, the velocity began positive, got less positive, and then became more negative, right? Okay. Now, some of you right now are going, wait a minute. When you throw something, the only force isn't gravity, right? Technically speaking, there is one other force, which is air resistance. That is not how you spell resistance. All right. We will, for the purposes of this class, pretty much always ignore air resistance. We'll talk briefly about it when we get to forces. But unless I say otherwise, if you're doing a problem, you can assume that there's no air resistance, which I know is super frustrating. But the reason that we do that is because air resistance is actually very complicated to calculate, and it takes some calculus. If you take the AP class next year, you'll learn a little bit about how to deal with air resistance. But even that really technically is just an approximation. Okay? Added to that, in most cases, the effects of air resistance are pretty minimal. Okay? All right. Hopefully I did the demonstration in class to help you see this the concept illustrated here on the slide, or explained here on the slide. But if not, we'll definitely do it when I see you next. So Galileo, Italian dude who lived in the 1500s, I should have checked my notes, discovered that all objects in free fall accelerate at the same rate. And that rate is called the acceleration of gravity. All right, now most books just use the letter G to represent the acceleration of gravity. I tend to try to use AG because it stresses the fact that it is an acceleration. Okay. When we get to AP, if you take AP, we'll probably switch over to G, but for a first year course, I really like to try to use AG instead of G because, like I say, it emphasizes the fact that it's an acceleration. All right, and so it turns out on Earth, the acceleration of gravity is negative 9.8 meters a second squared. All right, and then I guess technically, usually when people refer to G as a constant, usually people use the positive version of that. So that's sort of the magnitude, we would say, of the acceleration of gravity, and then it would be up to you to determine the direction, which obviously would be down. So then the question is down, positive, or negative. Okay, and as you know, we usually make down negative. Okay, so anyway, what all of this means is that anytime you drop an object on Earth, the acceleration will be negative 9.8 meters per second squared. Anytime you throw a ball on Earth, the acceleration will be negative 9.8 meters a second squared. Okay, because in both of those cases, the only force is gravity, and so it's in free fall. All right. Be aware, though, that this is specific to Earth. Okay, the acceleration of gravity is different on other planets and moons and suns and stuff. So here's a couple examples. On the moon, there's the acceleration of gravity. It's about negative 1.6. And on Jupiter, because Jupiter is a very big planet, there's sort of more gravity. So you have more acceleration of gravity, and it's about negative 25. All right, and then just remember, no air resistance. All right. Okay, so also, I spelled air wrong. We are not talking about RA resistance. Okay, so what all of this means. Anytime an object is in free fall, anytime you drop or throw an object, it will accelerate at negative 9.8 meters a second squared, which means every second the object's velocity will decrease by 9.8 meters per second. So let's see what that means. All right, so here on this slide, we've got 3 different examples. So in the first example, Roy's going to drop a ball. Oh, well, that means that the initial velocity of the ball is going to be 0. And because he's dropping it, it's in free fall, which means that the velocity is going to decrease by 9.8. So all I'm going to do is I'm just going to keep subtracting 9.8 meters a second. Okay, notice these numbers are getting bigger but more negative. All that indicates is that the object is moving down faster and faster and faster. Okay? All right, so there's your velocities in meters per second. Now, if we wanted to, well, I'm getting ahead of myself. Okay, so there we go. So that is what will happen if you drop an object. All right, now in the second example, Roy throws a ball up at 29.4 meters a second. So in this example, our VI is 29.4 meters a second. So that means at the instant that Roy lets go of it, the instant it becomes an object in free fall, the velocity is 29.4. And then, because it's in free fall, the velocity is going to decrease by 9.8. So as I did before, I'm going to keep subtracting 9.8. You get 19.6, 9.8, 0, negative 9.8. Why is it negative now? Well, we'll see negative velocity. Remember, those signs indicate direction. So for us, negative velocity means downward velocity. Oh, it's coming down now. So why was it 0 here? Well, let's see. Here it's moving up quickly, up slower, stops moving up. Now it's coming down. Now it's coming down faster. And now it's coming down faster. So all I did was I just kept subtracting 9.8. Okay? So here is this right here. This is the first time we've really seen, I guess that's not true, but one of the first times we've seen the advantage of keeping track of our signs on velocity and acceleration, right? Okay? Because this allows us to solve this problem in sort of one step, I guess. That'll make more sense once we start doing these with equations. All right? Notice that in both of these examples, the acceleration, in all three of these examples, the acceleration is negative 9.8 meters a second squared. The only thing that's changing is the initial velocity. All right, which brings us to our last example. So in this last example, Roy's going to throw the ball down at 29 meters a second. All right. So in this one, our VI is still 29.4 meters a second, but because he's throwing it down, we got to make it negative. So our starting velocity, at the instant it becomes a object in free fall, there's our velocity. And then after you let go of it, the only force is gravity. So you just keep subtracting 9.8. So you get 39.2, 49.0, 58.8, 68.6, 78.4, 88.2, and then I guess you get 98 after that. All right. All right, so that's the deal. And I guess this makes sense too, right? Because this is showing it moving down pretty quickly, but then it goes down faster and faster and faster and faster and faster, etc. All right, so I think that's it. It is. All right, how about that? 12 minutes. Bam. I'm going to take back that bam for less than 10 seconds. So what all that means is when you're solving a free fall problem, you automatically know your acceleration, right? It's automatically negative 9.8. So from there, all of the equations that we've learned in this chapter still apply. So you can still use your VF equals VI plus AT equation and still use those same acceleration equations. The point is we know the acceleration. Now, bam.